Recording in progress.
Okay,
Yeah. Also make the Zoom full screen.
how?
F11.
What am I doing?
F11.
Yeah, that didn't do it. I'm not a. You like,
You've done it before.
have I?
Yeah.
It's on the full screen, full screen. There we go. Okay,
Thank you.
no problem. Okay. So what we're gonna do is we're gonna continue with nucleophilic aromatic substitution. And I'm sorry for the video in mime yesterday. I must have covered the volume or something on my iPad when I made it. And then by the time that Professor McAteer told me, I did not have time to make another one. Okay, so I will get that up for you. It's just for your, for you to help you with the post lab stuff. Okay. All right, so what we did, so we were in chapter 17. And we looked at nucleophilic aromatic substitution. No, 18. Sorry, chapter 18. Yep. Okay, and I'm going to abbreviate that NAS. And what I started with, right, was the addition elimination mechanism. And this is what you're doing in lab this week. So with addition elimination, you need to have a leaving group, and that leaving group is going to be chlorine or bromine. You need to have electron withdrawing groups on the ring. And you would like them to be in the ortho or para position to the leaving group. You need a nucleophile, but it does not have to be a strong nucleophile. So what I mean is it doesn't have to be negatively charged. Okay. All right, so, and then we did the mechanism. Bless you. All right, so the first step is the addition step, where the lone pairs are going to add to the carbon with the leaving group, and then the pi electrons go on to the adjacent carbon. Okay, so this is the nucleophile adding to the carbon, bearing the leaving group. I'm just going to scroll so I can go straight across with the resonance structures. When the addition step happens, this breaks the aromaticity of the ring. Okay, so because the nucleophile was neutral, I have a positive charge on the nitrogen and a negative charge on the carbon with the nitro group. I could have gone the other way. I could have gone to this carbon. All right, it's just where my pi electrons were in the ring. So remember, with nucleophilic aromatic substitution, typically the intermediate or at least I'm going to say the charge on the ring is negative. Because when we do electrophilic aromatic substitution, what we're going to see is that the charge on the ring is positive when an electrophile adds. Okay, so when a nucleophile adds, you have a negative intermediate. All right, so now this charge can delocalize. All right, so we can see that that lone pair can go between the two carbons, and then we can put a negative charge on the carbon with the para-nitro group. I'm just going to consolidate the nucleophile for right now because we're focusing on the charge going around the ring. And then I've got one more where it can delocalize that way, and you get the charge out on the second ortho carbon. Okay, so that's the charge delocalizing to the 3 carbons of the ring. So it delocalizes ortho and para to the leaving group. Because we now have these electron withdrawing groups, okay, in the ortho and the para position, we have extra resonance structures. So the nitro group, this NO2 group, looks like this, where there's a positive charge on that nitrogen and a negative charge on that oxygen. So that when we delocalize, that nitrogen is still positively charged, but we put the negative charge out onto one of the oxygens. Okay, so you get extra resonance here. And then I'll show you again at the para position when that negative charge is there. So I did this last week. I just did it quickly because I was trying to acclimate you for the lab. And I had technical difficulties in the beginning of class. Okay, so in all of these reactions, when you do nucleophilic aromatic substitution, you're going to have these 3 resonance structures. If you have electron withdrawing groups in the ortho and the para position, right, you get these extra 2 resonance structures. Yep. So what I bracketed in orange, okay, those are the resonance structures that you get for nucleophilic aromatic substitution, where you have a carbon, okay, that has a negative charge, and that charge is delocalizing throughout the ring. What I have bracketed in pink, okay, are the extra resonance structure that you get if you have an electron withdrawing group in the ortho and the para positions. Okay, all of them, so I'll put a big black bracket, are resonance structures. Okay, so they all contribute. to the stability. So I'll zoom back out just in a minute. If you look here, I'll label this step 1. That's the addition step where I have that red step, that 1. Then what we have beneath it is the resonance of the intermediate. Step 2 is going to be the elimination step. So I'm just going to draw that first structure. Okay. So in the elimination step, the pi electrons go back in the ring. So we are regenerating the aromaticity of the benzene ring. And the leaving group leaves. Okay. Then what we have to do is we have to deprotonate this. If the nucleophile was negative, you wouldn't have to deprotonate. Okay. So I'm just going to get a little bit bigger. So now what we have to do is we have to deprotonate here. So let me just draw my hydrogen in. Okay. So you just take the pi, not the pi, the sigma electrons, and they go onto the nitrogen. So that's that deprotonation step. And here's your product. Okay. So that is how we do addition elimination. Yeah, there's just one product here. Join.
Where's that like one atom consumed with your strips?
Where's
In the first one?
this arrow?
Yeah.
So it's showing the electrons going in between to remake the pi bond.
Oh.
Okay, so here you're remaking a pi bond. Right. All right. The second type, the second way to do this is elimination addition. And you're going to have to be able to distinguish between the two. Right. So here, there are no electron withdrawing groups. And you need a strong nucleophile. You have a leaving group, which can be chlorine or bromine. and you're going to get a mixture of products.
Dr. Shaw,
Yeah.
for conditional elimination, is it always going to be one product?
Yes, because you're directly substituting for the leaving group. Grace, what was your question? Your question, yeah. Okay. Because that nucleophile is adding to the carbon that has the leaving group, right? So it's a direct substitution reaction. Okay. All right, so with the elimination addition mechanism, it's also known as the benzyne mechanism. I should say this, not only is it a strong nucleophile, but it's a base as well. So it's a basic nucleophile, okay? So you're looking at things like OH minus, OR minus, or NH2 minus. So I have my halogenated benzene. I'm going to treat it with sodium hydroxide and water. I'm going to heat it. All right, so that's going to be your first step. And that will substitute the chlorine. Okay. Then you're going to have a protonation step. To make it neutral. Okay. All right, so we're going to go through this mechanistically. So here, again, the first step is elimination. And this one, there is only one product just because you have the one chlorine, but I'll show you what happens when you have substituents on the ring. Okay, after we go through this basic mechanism. Okay, so first step is elimination. The base is going to abstract a hydrogen ortho to the leaving group. I could have gone to either carbon. I'm just choosing this carbon. So I'm going to take this hydrogen. The electrons are going to go into the ring and the chlorine leaves. Okay. So you abstract a hydrogen, the bonding electrons go into the aromatic ring and the chlorine leaves. You make what is known as a benzyne intermediate. Okay, so you have this triple bond in the benzene ring. This is a benzyne intermediate. It's very reactive. There's a lot of strain here. All right, so then the second step is going to be the addition step. So you have your benzyne. I could add to either carbon, okay? I don't have to add to the carbon where the chlorine was. This is why you get this mixture of products. Okay, so the nucleophile will add So it's going to add to one of the carbons of the triple bond. And then the pi electrons, all right, go on to the adjacent carbon. They're going to go on to the other carbon of the triple bond. You have water present. So that negative charge can abstract a hydrogen, and those electrons go on to the oxygen. Okay, so there's our product. Now, I don't normally deal with the inorganic counter ions for you, okay? But understand, right? So we added NaOH to start with, right? That was our nucleophile. And then we are regenerating NaOH. So this makes the reaction basic. So we're going to have a high pH. You have a basic solution. Right? We didn't go over phenol last semester, right? But phenol, the pKa of this hydrogen is around 10. Right? So this hydrogen can easily be deprotonated. This is the conjugate of phenol. Why do you think that pKa is so low for an OH group? What is significant about that conjugate? Think about what makes something a strong acid, right? We look at the stability of the conjugate. Chris.
We're asking about the pH, right?
I want to know why you can deprotonate this so easily. Or what's significant about this conjugate?
Well, what makes something a base or an acid is the amount of H plus to which I believe are like charged hydrogens, I believe. H plus.
Right. But we talked about things that lead to a strong acid. So you look at the stability of the conjugate.
It is a high concentration of H plus, I believe.
Right, but why? I want to know why. Just because there's a why, there's a reason. Okay, Joy. There's resonance. Remember the stability things we looked at? We looked at the size of the atom. I think I even wrote them down the other day when we were talking about aromaticity. We looked at the electronegativity. We looked at resonance. We looked at induction. And we looked at S character. You have resonance here. Okay, that negative charge can delocalize. So that's why phenol can be so easily protonated, right? Because of that, because we want to keep it neutral, right? That's why I'm just going to scroll up, but then I'll write it down, okay? That's why in this second step, you have to acidify, okay? It protonates it. If we kept the solution basic, then what we would result in is this negative OH group, okay? So here, right, that phenol, this OH, okay, can easily be deprotonated. So you need to bring the pH to neutral with HCl. Okay, in a separate step. I'm saying this too, because for those of you who are in my Thursday lab, I got really pissed. I don't know if this is going to be on recording right now, but oh well, okay. So I had a thesis student that did not follow directions and did not neutralize their solution. So we might do reactions in this, we'll do a Fischer esterification where you need an acid catalyst. That acid catalyst is in the form of very concentrated sulfuric acid. And if you do not neutralize it, and then you put your sample on the IR, well, guess what? You corrode the metal on the detector, okay? So it's really important. It's not just trivial when I say you have to add acid and bring something to neutral, okay? All right. So that's the simple mechanism. When we have a substituent on the ring, that's where you're going to get this mixture of products, okay? So now I have a methyl group. I don't just have the single leaving group. I'm going to add my basic nucleophile.
Before we start this, the products of the last one without the substituent is.
It's just the single product. It's just the phenol, right? Because there's nothing else. Even if I had, so I'm going to go through the mechanism with the substituent, but even if the OH group added to that carbon that I've highlighted in purple, you'd still get the same thing because there's nothing to, there's nothing else on the ring, right? No matter where you put that OH group, it's the same. Okay. So here, what I'm going to do is I'm going to write the reactions down and then the products, and I'll show you why you get the two. So again, we'll use the same nucleophile. Just put the heat there. And then in the second step, again, you have to protonate. I feel like I'm sorry, I don't remember off the top of my head the last couple of reactions we did in the fall, but a lot of the reactions, particularly where you do use something that's basic or acidic, you have to bring it up to neutral in the end. And that usually will cause your product, your organic product, to precipitate. So it's like a win-win, right? You're neutralizing it, and now you have a nice precipitate that you could filter out and not have to run one of those columns that take forever. Okay, so the two products that you have here are going to be where you have direct substitution or you have reaction at that other carbon. So what I want to do beneath is just, again, show you how this happens. So that first step, again, is the elimination step. So your OH group is going to take the hydrogen, the electrons go in between, and the chlorine leaves. You have your benzyne intermediate.
Dr. Sapper,
Yes.
you only get the benzyme intermediate with this type of reaction?
Yes. Okay. So it's where, so this is where, again, so you're going to have to look at the rings and what's on the rings. The key here is no electron withdrawing group. If you don't have an electron withdrawing group on that ring, it has to go by this elimination and addition. If you have an electron withdrawing group on the ring, then it can go by addition elimination. Okay. All right. So now my OH minus can add. If I add to the carbon where I've indicated with the blue arrow, I get that first product that I drew where it looks like the chlorine was directly substituted. Okay. I'm not going through the rest, okay? Understand I simplified this. If the OH group adds to where I indicated with the pink arrow, right, because they're equally reactive. Then I get that second product. Okay. So when you have a substituent on the ring, that's when you can get a mixture of products.
You're supposed to show both, right?
Yes. Okay. All right, so if I say to you, so I want you to draw the product or products and indicate, bless you, if it's addition, elimination, or elimination, addition. I'm just going to give you one more example to do this with. Yes.
What determines if the hydroxyl group goes to the top of the carbon on the right? You know how you get both products?
If it goes to purple or pink. All right, so you can have some control if there's steric hindrance where the leaving group is or next to the other one, next to the pink one. But in this case, you probably get equal amounts, okay? Okay, so you have two examples here. So what you need to do, okay, is determine, draw the product or products, and then indicate if it's addition elimination or elimination addition. All right, so I'll give you a minute or two to do that. Haven't decided yet. You definitely have to know the electrophilic addition to a diamine. And you definitely have to know what I'm going to do after this with the electrophilic aromatic substitution. I have not decided if I'm going to make you know this one. All right, so if you look at these, so Gabriella asked me if you're gonna have to know this mechanism. Now, you have to know it in the sense that on a multiple choice, like you would have to be able to, like, so for example, if I gave you your starting material and I gave you the reagents, and then you'll see it a couple of ways, okay? So the first one is addition elimination. Sorry, is elimination addition. See, now I'm even. Okay. You're gonna have two products. The second one is addition elimination. I'm going to explain a little bit further too, and then give you the context of how you'll see this in multiple choice. Okay. All right. So you could see this in multiple choice where I give you that, and then you have to pick the products, right? So you've seen those things on homeworks where it's pick the products. Is it 1 and 2? Is it 2 and 3? Okay, so you'll have that option. Another way that you could see this is if you could have to pick, right? I could say your choices could be addition, elimination, elimination, addition, electrophilic aromatic substitution. So you're going to have to be able to distinguish between these mechanisms. Okay. How you distinguish them is if you look at that first one, okay, so with elimination addition, and I'm going to scroll because I just want to add it to our list. Okay, you have to have a hydrogen adjacent to the leaving group. If there is no hydrogen adjacent to the leaving group, as there is in the case beneath this, it's got to be addition elimination. So there's no hydrogen adjacent to the leaving group. All right, that's your first thing that you can look at. So I just want to go add that to our list because I made lists. Okay, so here you have to have a hydrogen adjacent to the leaving group. Okay. And when I started lecture, I gave you the list of things for addition elimination. So if I go back here to my problem, if you look at that first structure, there are no, bless you, no electron withdrawing groups on there. Okay. If you look at the second one, there are electron withdrawing groups on there. So again, that also clues you in as to which mechanism you're going to choose. Okay. All right. So that's it for nucleophilic. Grace.
So for the second one,
Mhm.
because the NO2s are not both para and ortho, you're not going to have those extra structures, right?
They're both ortho to the leaving group, so you would have the extra resonance structures.
Just not that they have to be both para and ortho.
Correct. It's ortho or para. It's an and or, not an and. Okay. All right. So that's it for for nucleophilic aromatic substitution. What I would like to do now is electrophilic aromatic substitution. All right, and so I realized, I was going through kind of like the timeline again with somebody in office hours. So I will finish up 18 this week. All right, so I'm going to start it and I'll finish it Thursday, right? I might move on to 13. I'm not positive. We'll just kind of see how it goes. But regardless, I will start 13 on Tuesday. I actually really don't need 2 days to discuss ethers. I just kind of built it in. So Tuesday is the last day of new material next week. All right, so that's it. It's today, tomorrow, Thursday, and then Tuesday. And then that's it. Then we're pretty much reviewing for exam 1. And you have 2 review sessions. You have one that Thursday next week, and then you have the Wednesday, that recitation. Okay, but that one will be via Zoom. Yeah,
That's what's gonna ask, the Zoom, is it next week or the week after?
the week after. It's President's Week.
Okay.
Okay. All right. All right, so for electrophilic aromatic substitution. Okay, and my plan is to Zoom. All right, I'm just gonna say right now, I really have no idea what my internet connection is gonna be like, so I hope I can Zoom. All right, so we've done electrophilic addition already this semester, but just to kind of recap from what we did in the fall, if you have a double bond and you add an electrophile, you substitute for the hydrogens and you add to the, you add to the double bond. So this is just electrophilic addition. That doesn't work when you have benzene. These do not react as individual double bonds, because you have this aromatic ring. The bonds do not react like isolated pi bonds. Or even the conjugated pi bonds, right? We did electrophilic addition to a diene, right? All right, so instead, what we have to do is we have to add a catalyst to get this to work. So if we have benzene and we want to halogenate the ring, we have our Br2, but then we add FeBr3, which is a Lewis acid, which means it can accept electrons. Okay. And we will be able to halogenate our ring. All right, you will have to know this mechanism. All right, so this will be a possibility, absolutely, for a part 2 where you are drawing out the mechanism. So we have our benzene. All right, and you have your hydrogen there. I'm going to do this generically first. All right. So you have an electrophile. I'm going to show you how to make the different electrophiles, like how to make a bromine electrophile, how to make a nitro group one. But we're just going to go through this generically first. Okay. The pi electrons go after the electrophile. So notice, okay, that the electrophile is going to substitute. If you look above here, I'll draw the hydrogen up here. It's a direct substitution for a hydrogen. Okay. I said this to you before, when a nucleophile adds to a ring, you get a negatively charged intermediate. Okay. When an electrophile adds to the ring, we're going to get a positively charged intermediate. So we can have resonance. Where we delocalize this charge around the ring. Okay. But notice the charge, okay, is not landing on the carbon with the electrophile. So this is just to get you to, sometimes you have to pause because you just draw resonance structures and you just keep going, right? That positive charge is not hitting the carbon with the electrophile. I'm also saying this to you because when you have this as a part 2 problem, you are able to go back to your notes, okay? So I get it, and if you're doing this on multiple choice, you got to do it committed to memory. But that part 2 is the opportunity for you to go through your notes, right? So now, I mean, between these videos, okay, there's really no reason to not get these right, okay? Then, okay, you're going to have the hydrogen leave. So here we are going to regenerate the aromaticity. So remember, we're going to deprotonate the carbon that has the electrophile. It's a substitution reaction. So what we're going to do is now I'm going to give you a series of electrophiles and a series of reagents. And then we're just going to go down the list. Okay. So we are going to learn to chlorinate, brominate, nitrate, acylate, and alkylate benzene rings. You sometimes might see aluminum as well. So these reagent combinations allow us to generate an electrophile. Okay. All right, so the first one I'm going to go through is chlorination. But I'm going to put in parentheses bromination because it's going to be the same exact thing. So we have chlorine. And if you draw the complete Lewis structure for chlorine, you see chlorine has those lone pairs, those non-bonding electrons. Right? Your halogens can donate those non-bonding electrons. Okay. We are going to see that halogens, particularly your diatomic neutral halogens, are weakly electron donating. So I have iron trichloride, right? So this is deficient in electrons. That is why it's a Lewis acid. It can accept electrons. So it can accept those electrons from the chlorine. Now we'll have a negative charge on our iron and a positive charge on that chlorine. This complex will break down so that these electrons go to that positively charged chlorine. And you get Cl plus FeCl4 with a negative charge on the iron. Now I have my electrophile. Then the mechanism is going to proceed as I showed you that generic mechanism. You have your benzene. You have your chlorine electrophile. The pi electrons go after the electrophile. I recommend drawing the hydrogen in so you know what you're going to eliminate. So there's my intermediate. Again, that positive charge can delocalize around the ring. But it doesn't go Okay, to the carbon with the electrophile. Our Lewis acid, right? Well, now it's a base because it has electrons to donate. It can take this hydrogen and the electrons go back into the benzene ring. We've added chlorine to the ring and we get HCl and we regenerate our catalyst. Okay. What you need to know, right, as far as you drawing this out, you have to be able to. You do not have to show me how you make the electrophile. You just have to know what the electrophile is, okay? So if it's chlorination, understand that the electrophile is the Cl+, okay? If it's nitration, know that the NO2+ is the electrophile. I'm going to show you in each of these cases how to make the electrophile, but from a mechanistic standpoint, you don't have to draw it. So this is going to be the first step when you have to show an EAS mechanism. The ring and the electrophile. Understand that ring is going to get more complicated. Okay, we're going to put substituents on that ring and we're going to use aromatic heterocycles. All right, but whatever the EAS mechanism is, the first step is that ring and the electrophile. Okay. Then what you're going to have to show is this resonance and you have to show every resonance structure, because what we're going to see is again, when we put substituents on the ring, sometimes we can go beyond these basic 3 structures. Okay. And if you have an electron donating group on the ring, it's going to behave differently if we have an electron withdrawing group on the ring. For 3, you just, actually, let's do it like this. You just have to show the deprotonation. You do not have to show the base that's doing the deprotonation, okay? Because it'll change depending upon what you're putting on the ring. And I'm not going to make you memorize every base that forms, okay? So you do not need the specific base. And then you have to show the products. Sorry, the organic product. Okay, you do not need to show the inorganic products. Okay, Gabriella and then Shane.
Say you don't need to show the base. How would you would just like write in that it's deeper?
No, you would just draw that blue arrow. Okay. Shane, that was your question? Okay. All right. So that's your same thing. So if it's bromination, it's just the Br+. Okay. All right. Do we have any questions with this? All right. For your nitration, So generically, you'll have your aromatic ring, you have your HNO3, your H2SO4, and you're going to put a nitro group on your ring. Okay. So in order to generate a nitrate electrophile, you do not need to know this step. All right, you do not need to memorize this. I'm just showing you how you draw it out. Okay, so you have nitric acid, and then you have sulfuric acid. You're going to deprotonate the sulfuric acid. When you do that, okay, when that nitric acid takes that proton, what did I just make? What did I make? Water, which is a good leaving group, right? We did that towards the end of the fall semester. So the water leaves. And now I'm left with my electrophile. Okay, so that's how I make my NO2 electrophile. So the same chemistry is going to happen. Okay, so you just pretend that this is E plus, and you go through the mechanism the same way. Same resonance, same thing. Okay. All right. For your acylation, it's known as Friedel-Crafts acylation. Again, you have your benzene ring. This is called an acid chloride. We will learn about them in more detail in the later chapter. And here we have our aluminum trichloride. Your net result is to add an acyl group to the ring. I'm going to show you again how to make the acyl electrophile, but you do not need to know this. Okay, I have that lone pair, similar to what we did with chlorination. On the chlorine, it can donate to the electron deficient aluminum. So this is very similar to what we saw before, all right? But instead of having that second chlorine, I have that carbonyl there. You break that bond. And you get your acyl electrophile. Okay. Same chemistry that we did. So again, this is just E positive. Okay, that's the same electrophile. All right. If we want to alkylate, it's Friedel-Crafts alkylation. You have your benzene ring. You add an alkyl halide. Right, that RCl is an alkyl halide. You have your aluminum trifluoride. And then you can add that R group to the ring where you can alkylate the ring. All right. Again, I'm going to show you how to make the electrophile. You do not need to know this. So you have your alkyl halide, you have your Lewis acid. Same thing that we saw above. You're going to break that alkyl chloride bond and you get R positive. Now, while this looks very simple, what is R positive? We've encountered this before. What is it when you have a positive charge on an alkyl group? What do we call that? Starts with a C. Carbocation. What do carbocations do? What's the problem, AJ? They have resonance, but what's the problem with a carbocation? Like, think about it when we were doing reactions. A carbocation is going to what? It's going to rearrange, right, into something more stable. Okay, so because of this rearrangement, you can't always get the desired alkylation. So I'll show you an example of this. If we have benzene and we add our alkyl halide, one, two, three. Does everybody see that that's the carbocation that gets generated? Okay. Before this can react with our benzene ring, this primary carbocation is going to rearrange to give us a more stable secondary carbocation. Now, this is what reacts with our benzene ring. And that is what we get. Okay. So we're going to have to come up with strategies, right, to mitigate this. If this is the desired product, we need a different strategy. Okay. I can spell. Okay. All right, I'm going to stop here. I do want you guys, all right, I know I owe you a homework. What I'm going to do is, all right, let me just, well, yeah, let me go pause the recording.